Hi, everybody. We are back to continue our discussion related to the sampling distribution, which is, again, different than the population distribution. So we're going to use really a different bell-shaped curve in this segment to think about the sampling distribution that is generated when you look at subsets of elements sampled from the population distribution. And we concluded the last segment by looking at this metric known as the standard error. And the standard error, this is the standard deviation of the sampling distribution, as opposed to sigma, which is the standard deviation of the population distribution. So we're giving them two different names here. In order to calculate the standard error, we take the standard deviation of the population and divide by the square root of our sample size. And again, this told us that the sample mean was a consistent estimator since its standard error approaches zero as n gets arbitrarily large. So to clarify the difference between these two, again, the standard error really talks about the variability of sample means relative to that population mean, right? Every time we resample different samples, that sample mean has a little bit of noise implied in it. So this is variability about the point average here. The standard deviation, on the other hand, is measuring the variability about an actual data point, about an actual element from the population, okay, not from the sample. The standard error of the mean is never larger than the standard deviation of the associated population mean. Okay, there is one particular case where they can be equal to each other, and that is if your sample size is equal to 1. If n equals 1, then those two things will be the same. Otherwise, the population standard deviation is going to be larger. Now, we talked about this idea known as the central limit theorem a little bit in the last segment by looking at this experiment where we started with a population that was not normally distributed. We resampled from it, and we showed that the distribution of the sample mean turned out to be fairly symmetric and bell-shaped. So we're going to look at this result in a little bit more detail. And we're going to start off with an associated result, and that is, if the underlying population is normally distributed, then the sampling distribution is also going to be normally distributed. And in fact, it will have the same center. It's going to be centered at the same point, okay, mu. But the difference is in the standard deviation, in the spread. Okay, and we said before the normal distribution, if that is the population on the left here, that is going to have a wider standard deviation than the sampling distribution, the distribution of those sample means. So this theorem says essentially if the population is normal, then when we sample from it, that distribution will look relatively normal. But we're going to see an even more interesting result, which we kind of took a peek at in that experiment we ran in the last segment, that even if the population was not normal, if we sample from it and our sample size is large enough, the sampling distribution of the mean will still be normal. And again, the big benefit of knowing that the sample means are normally distributed is that we can still use the Z transformation in order to compute probabilities underneath that standard normal distribution, with one small adjustment, and that small adjustment hopefully is fairly easy to see here, and that is, instead of dividing by the standard deviation, we're now dividing by the standard error here. And so instead of x minus mu just over sigma, we're also dividing by that standard error, the standard deviation of the sampling distribution instead of the standard deviation of the population. Why? Well, because we're using the sampling distribution in this case. Okay, so let's go ahead and apply this idea here to a mini case study. And the situation we're going to look at involves a manager at a local Starbucks that wonders how a particular promotion has affected the business. And prior to running the promotion, we can see here that the customer spent an average of $4.18 on iced coffee with a standard deviation of 84 cents. And a month after the marketing period ends, and the manager, she surveys 50 of her iced coffee customers and finds that they spent an average of $4.26, which is, an 8-cent increase on on what the average was prior to running the promotion, which maybe makes it seem like the promotion was fairly effective. It makes it seem like the promotion was fairly effective. However, we know that that 4.26 figure is somewhat sensitive to the exact 50 people that were sampled, okay, and randomly samples those 50 people. If she had randomly sampled a different group of 50 people, then that average is probably going to be a little bit different than $4.26. So the question here is the promotion effective, or is this just a little bit of noise from the sampling process that we are seeing here, and the promotion's not really effective? So this type of question is actually a really good motivating question for what we're going to move into in the coming weeks on interval estimation and hypothesis testing, where we're going to look for testing a hypothesis to see if there is a statistically significant effect of something like running a sales promotion. So the question we're going to think about for now here in the scope of our sampling distribution discussion is, without the promotion, how likely is it that customers would spend an average of $4.26 or more on iced coffee? Okay, and again, we know several parameters here. We're going to assume that the population distribution is centered at $4.18. That's the population of sales prior to running the promotion. The standard deviation was 84 cents. Okay, and we're going to go ahead here and look at our sample details. We had 50 folks in the sample that we had randomly sampled. And the sample mean of those 50 folks was $4.26 spent. And again, the question here is really asking the following: what is the probability that the sample mean would be larger than $4.26 if that sampling distribution prior to the promotion was centered here at $4.18? So the probability we're being asked for is essentially an upper right tail probability. Okay, assuming that the sampling distribution is centered at $4.18 with a standard deviation of 8.4, question is, what is the probability of observing expenditure greater than or equal to $4.26? So that is what we need to find here. And you might be thinking, well, that procedure sounds a lot like what we had dealt with the normal distribution in the previous segments. And you couldn't be more right. There is one very, very small difference, and that is, instead of us calculating the Z-score like we would have for a normal population, we're now going to calculate the Z-score incorporating the standard error term in the denominator, because we're dealing with a sampling distribution. That's the standard deviation of the sampling distribution, instead of just dividing by the standard deviation of the population distribution. So that is the difference here. Okay, so the approach is going to be very, very similar, right? Assuming that population was normal, our sampling distribution is normal, so we can go ahead and use that standard normal table, and we're going to convert our X value into a Z value. Okay, so we can go ahead, we can demean it, take 4.26 minus 4.18, and we're going to divide that by the standard error here, which is 0.84 over root 50. And when we do that, we will have converted our X bar into a Z-score of 0.67. And so we've started an X space, we switched our problem to Z space, and now the equivalent problem here is, let's find the probability that Z is larger than 0.67. So that is going to require us to switch to our standard normal table and identify the value associated with 0.67. So let's jump up here to our standard normal table. Okay, we can see here is the row corresponding to 0.6. Here is the column corresponding to 0.7. So the probability that determines the interior probability, right, between 0 and Z is 0.2486. Right, so we're going to have to subtract that from 0.5 to get that upper tail probability, just like what we have been doing with the population distribution. So this element doesn't really change here. We figured out that value from the table. We're going to subtract it from 0.5, and this gives us the value in that upper tail, which is a little bit larger than 25%. Okay, so the conclusion here is without the promotion, the likelihood that somebody would be spending an average of $4.26 or more would be about 25%. Okay, which is, you know, pretty reasonable, I suppose. And some might conclude that perhaps the campaign was not that successful if even without it, there was a 1 in 4 chance that somebody would be spending that much money. Okay, so let's go ahead and take a look at a few more applications here. Okay, in this next example, Nike's annual report claims that an average American buys 6.5 pairs of sports shoes per year. It's about 13 shoes if you think about it. Suppose the population standard deviation is 2.1 pairs and that a sample of 81 individuals was randomly chosen. And the question up in the stem is, what is the probability that the sample mean is between 6 and 7 pairs of shoes? So formally, we want to describe this as a probability problem. We're being asked, what is the probability that the sample mean here, the mean sample of shoes from the sample of 81 is between the values of 6 and 7 pairs. So we're going to do the same thing. We're going to convert those thresholds there, 6 and 7. We're going to convert them to Z values. Hopefully you'll note that 6 and 7 are on equal sides of that mean of 6.5. So when we do this, Z1 and Z2 are lower and upper bounds actually have the same magnitude of 2.14. And again, at this point, we could go ahead, we can take a look at our standard normal table, and we're looking for a value of 2.14. So we're going to scroll down here. Here's 2.1. Here we are. And we want 2.14. Here's the 0 column. 1, 2, 3, 4. That's 2.14. Corresponds to this probability 0.4838. And we're going to have to double that, okay, since we're on equal sides of the symmetric bell-shaped curve, right? There are 2.14 standard deviations above on the right side and 2.14 standard deviations below on the left side. So let's go ahead and incorporate that into our analysis. And we double that probability, we get a likelihood of 96.76%. That the average American in this sample would have somewhere between 6 and 7 pairs of shoes from that 81 size sample that was taken. Now, the interesting thing about the central limit theorem, as I mentioned earlier, is that if the population is not normal, okay, we can still generally make the assumption that the sampling from that population, the distribution, the sampling distribution generated from that population will still be normal. Okay, provided one important condition is met, and that condition is that the sample size here is sufficiently large. And we'll talk about how large is large enough in just a moment. If this condition is met, then the sampling distribution will be normal. It'll have the same center as the underlying population distribution, regardless of the shape of that distribution. It'll be centered at the same place, but the standard deviation of the sampling distribution will be governed according to the standard error here. Okay? So very familiar. So let's go ahead and take a look at a few simulations, at least the visualization results from those simulations. So in this first case, I'm going to show you a few pictures here, and as you move down the column, okay, what we're going to be doing is starting at the top with a particular oddly shaped population distribution. And then we're going to see that as we sample from that distribution, right, as we move from top to bottom here in this picture, what's happening is that the sampling distribution looks more and more normal as the number of observations increase. So note the shape of the underlying population is very, very weird here. And it's almost like a negative bell shape, an upside down U, okay, or rather a regular U. But that's a very weird population shape. And as we increase that sample size, we go from 2 to 6 to 30. Okay, resampling 30, 30, 30, 30, and plotting the means. That's what we're doing here, is we're looking at the histogram of those means plotted. Okay, as long as we have enough observations, the sampling distribution will look normal. Okay, and we can see that again here with a slightly different but oddly shaped population distribution. So up top here, we have the cheese wedge distribution, a triangular distribution. And again, as we move from top to bottom here, we are seeing that sampling more observations, okay, generates a sampling distribution that looks more normal. And again, this applies regardless of the shape of the underlying population. Here we're dealing with a rectangular population distribution, a uniform distribution, if you will, which actually corresponded to the case that we had looked at in the last segment, where we had individuals A, B, C, and D. They all showed up with equal frequency in the population. And then we generated all those different samples, and we looked at the sample mean distribution and saw that it tended to look normal. So again, this is a pretty interesting result, no matter what the shape of the underlying population distribution is. Okay, we can make this assumption that as long as the sample size is large enough, the sampling distribution of X bar will be described by a bell-shaped normal distribution. Okay, so that's the idea here. As N gets big enough, that sampling distribution becomes almost normal regardless of the shape of the underlying population. This is a super important result in statistics. Okay, it tells us that we don't have to worry about all these other different types of distributions with respect to the sampling mean. We can just generally deal with the normal distribution, provided we have enough observations. Now, what happens if we don't have enough observations? We will get to that in the next segment on interval estimation. Now, how large is large enough? What is that threshold? It turns out for most population distributions, as long as you're sampling about 30 observations or more, the sampling distribution will be nearly normal. If the population distribution is symmetric already, and maybe not normal, but maybe symmetric, like a uniform, a flat distribution, or a triangular distribution that's perfectly symmetric, then it turns out you need a lot fewer observations, about half as many, at least 15, for the assumption of normality in the sampling distribution to be reasonable here. Okay, and again, if the population distribution is already normal, then the sampling distribution for the mean will always be normally distributed here. All right, so we're going to go ahead and conclude with one more application of the central limit theorem. And we're going to take a look at some very strongly skewed population data for waiting times at airport security, with a mean wait time of 2.983 and a standard deviation of 2.451. And so we can see here the population is very, very skewed. Does not look like a bell-shaped curve. Very skewed, positively pulled to the right. That right tail is getting pulled over. So this is not a normal population. Okay, but here's what we're going to do. We're going to sample from that population. We're not going to look at all those individuals. You can see here, they're in the thousands almost, right? If we added up the size of all those bars, but we're going to go ahead and sample enough. We're going to sample 36 individuals randomly at airport security. And it's going to be okay for us to assume that this sample mean is centered at 2.983 minutes with a standard deviation of 2.451 minutes, because we have at least 30 observations here. Okay, we got 36, we beat that threshold. So even though we're dealing with a lot of skewness here, it does not look like a normal distribution. Even though we're dealing with a lot of skewness, we're going to be able to exploit the central limit theorem, transforming this problem into a very familiar situation. And let's go ahead and think about asking, what is the probability that the sample mean is going to be between 2.5 and 3.5 minutes? Okay, what is the probability the sample mean is between 2.5 and 3.5 minutes? So here's what we know. Okay, we know that even though the population is skewed, its mean will correspond to the center of the sampling distribution. And we are also given the population standard deviation here of 2.451. We have 36 observations, and we're interested in two particular X thresholds, 2.5 minutes and 3.5 minutes. And again, even though the population is not normally distributed, the central limit theorem can be applied here because we have at least 30 observations, implying again that sampling distribution for X bar for that sample mean is approximately normal, and we can get away with using our standard normal table via the Z transformation. So what are we going to do here? Same thing we've been doing. Okay. We're going to convert our problem from X space into Z space, noting that our sampling distribution is centered at 2.983. And we can compute the standard error, which again is the standard deviation of the sampling distribution, which is sigma over root n. So we can now describe here our sampling distribution, given that we had started with that population distribution, right? We had this really skewed population distribution, but we took a large enough sample, okay? And it's okay to assume this is normal because we had 36 observations above that 30 observation threshold. And we are being asked for that probability in the pink region between 2.5 and 3.5 minutes. And what are we going to do next? Well, we're going to transform our problem from X space into Z space using the Z-score. So we're going to go ahead and convert X1 and X2 into the associated Z values using, again, the standard error as our normalizing factor here. So Z1, we're going to take 2.5, subtract out that population mean, divide by the standard error, and we should get a value of minus 1.18. Z2, the upper threshold corresponding to 3.5, gives us a Z-score of 1.27. So at this point, you should be able to go to your standard normal table. You're going to have to find the probabilities associated with Z values of 1.18 and 1.27. And we've now transformed the problem here into finding the Z that is in between those two thresholds. So once I get the table values for each of those, I'm going to go ahead and add them together. Remember what the table gives us. The table is going to give us, so if we were to plug in here, if we were to go ahead and substitute 1.27 Z value into our standard normal table, the standard normal table is going to tell us this probability, okay, corresponding to a Z value of 1.27. So we would have to add that to the associated table value that we would get for 1.18, which remember is the same as negative 1.18 since the bell curve is symmetric. Okay, so that's what we need to do. And we go ahead, find those table values. So take a moment, try that on your own, add them together. If you need to pause the video, please take a moment to do that. And you should wind up with a value of about 78% here, so 0.7790. All right. Let's go ahead and check out one more example here, and then we'll summarize by kind of wrapping up our discussion of the central limit theorem, this very, very strong result that allows us to exploit that normal distribution in many, many situations. So let's go ahead and consider the following situation where the rent for a one-bedroom apartment is positively skewed with a mean of $2,200 per month and a standard deviation of $250 per month. Question is, what is the probability of selecting a sample of 50 one-room bedroom apartments and finding that mean to be at least $2,300 per month? Okay, so formally we're asking what is the probability that the sample mean is greater than or equal to that threshold value, which means they are asking us again to find an upper tail probability. So how are we going to do this? Well, let's go ahead and convert that threshold 2,300 into a Z-score. So we subtract the 2,200 mean, divide by the standard error, which is the 250 over square root n term here, and that'll give us a Z value of 2.83. Okay, so at this point, we're going to go ahead, we'll go to our standard normal table, and we want to find a Z value of 2.83 and look at the probability associated with that Z value. And again, the table is going to give us the area, not in the upper tail, which is what we want to find, but it's going to give us this shaded green region here. Okay, which means once we get that, we'll subtract it from 0.5 to wind up with our final answer, that upper tail probability. So let's go ahead here and we'll switch to the Z table and find that Z value for 2.83. So here we are. Here is our 2.8 row. We got 0, 1, 2, 3. So we get 0.4977. That's 2.83 Z value, corresponds to a probability of 0.4997. And again, that was that green shaded region we had drawn on the slide a moment ago. So we're going to go ahead and subtract that from 0.5. And when we do that, we will wind up with our final answer here, which is a very, very small probability, 0.0023 in that upper tail, which is choice A. Now, just to kind of wrap up our discussion here, when can you use the central limit theorem? Well, let's start here with this little flow chart. If the population is normal, then the sampling distribution is going to be normal. Okay. However, if the population is not normal, then we're going to ask, well, how big is your sample size? If your sample size is sufficiently large, okay, how large? Well, if n is bigger than 30, and that's a yes, then we're going to assume here that the sampling distribution is normal, and we can apply that central limit theorem. However, if the answer to this question here is n greater than or equal to 30, if that answer is no, then the sampling distribution may not be considered to be normal, and we're going to need a little bit more information. We're actually going to use a slightly different distribution to capture that situation, known as the student t-distribution, but you'll see more on that in the coming segments. Hope you enjoyed. Stay tuned and have a good one.